about the homework that you do today, or the final exam, or the homework you just got back. One thing about the homework you just got back was, on the grad problem, I was looking for the normal equations to be solved, actually. Similar as what they did in the book. And on the previous problem, about 8.3, nobody found the Boston number of cases interaction. There was an or distance interaction. Maybe it was distance interaction. I forget which one it was. I might have written that wrong on the problem. Let me see. What did I do with 8.3? Yeah. You see, maybe I don't understand why nobody put any interactions. I know there's a lot of terms, but I don't understand why nobody put interactions on problem 8.3. Let's see, what was it? Yeah, it was the distance Boston interaction. I have that wrong. It was the x2 Boston interaction. In Boston, I believe it was Boston. Maybe I have the wrong city. It was x2 D1. What was D1? I think that was the first city. San Diego. What do we got going here? Yeah, x2 D1, San Diego. Is that how I did it? It's kind of tricky to figure out the reference to where the actual... I have both things wrong. You know, not only do I have the wrong variable, but I also have the wrong city. 8.3. It says refer back to section 4.2.5. I have to hunt down, collecting in 4 cities: San Diego, Boston, Austin, and Minneapolis.
I didn't do interactions. The rest of the problems in the section specified when they wanted interactions.
I know. But is there any indication that delivery site is an important variable? Well, not for intercept, but you have to think about what's going on with this indicator and this problem. All you're actually doing is, by not putting interactions, you're assuming that the lines all have the same slopes, or planes all have the same exact slope parameters. All they're doing is intersecting at different places. Okay, so by only putting the indicators and no interactions, you're assuming that the response in the 4 cities just looks like parallel planes. Okay. You know, and then the only difference is there's a different intercept for each of the planes. It's not reasonable. So you're not getting anything for you're not getting any kind of interaction at all. So you need to consider there's actually 6 extra terms, right? Because there's 3 indicator variables and 2 numeric variables. So you consider all the cross classifications just to get different planes. I have possibly 4 different planes, right? So that means I need lots of stuff. Okay. I need a total of 12 parameters to get 4 planes. I need 2 slopes and 1 intercept for each plane. So most of them, okay, maybe most of them are pretty much parallel, but there's one that's not. Okay, because it turns out that I don't know if I forgot to put this on the website, but if you do the analysis, you get a t-statistic of something like 6 for x2 D1, where the way I coded D1 so you're certainly not going to do, I mean, if I'm asking you to do problem 8.5, you need to put an interaction term in there, as I'm pointing out. Okay. There it's more obvious because there's only 2 types. I mean, you don't have to put as many terms in the model. Here, you just be afraid to put a whole bunch more terms in the model, it looks like. I don't want to put 6 more terms in the model. That's ugly. Okay? But you can't see anything unless you put some more things in. Okay? Let's see. So I had x2 was distance, and I had d1 I had to be it was 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7. 7 zeros. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 ones. And then zeros after that. Okay. And I had the data ordered exactly the same way that they did, 4.2.5. Let's see. Let's make sure I get the right city. Okay, so x2, let's see, what was the coefficient? What was the reduced? Give me your x2 coefficient from your papers, people that just did this. 0.010833. 0.010? The x2 coefficient is 0.0108. Is that what you're saying? Okay, without interaction. Okay. Okay. And what was the t statistic? 2.86. Okay. Basically, what happens is, and t stat is 2.86. What happens is, then if I put in x2d2, if I put in with x2d1, okay, interaction only. It's the only one that really counts. If you look at all of it, okay, it's the only one that sticks out. Okay.
You wrote on mine, show the Boston x1 interaction.
I made a mistake. It should have been San Diego x2 interaction. Okay. So it's actually the distance, which seems kind of counterintuitive, but apparently something's going on in that particular town with the distance that they had to go. Okay. To the machine. I don't know why, because of some business they're doing there. So what I have is that x2, the x2 coefficient is basically gone to 0.002, and the x2 d1. So I have all these other ones in here. They still have d1, d2, d3, but an x2 d1 is now 0.0145. Okay. And that's the t statistic here. Now the t statistic is not significant. The x2 coefficient itself is not significant. So basically it doesn't matter in the other cities. The distance doesn't matter at all, roughly speaking. 0.788. But in San Diego, assuming we have the town right, the t statistic is 5.92. Okay? So it matters a lot in San Diego. Okay, the x1 coefficient was 1.7. How much was it in yours?
I'm sorry, I was just saying for cases. The x1 coefficient was 1.77.
Yeah, it's the same, 1.76 here. So it goes to x1 is 1.76. It doesn't change at all. Okay. So in the other cities, the distance didn't matter. So you saw how distance was a weak variable in general, but that's only on average. In fact. It's extremely weak if you take out San Diego, and then it's extremely strong if you consider only San Diego. Okay, so that's what's going on. It did matter what town you were in terms of how the distance affected it. So anyway, it's just a warning to if you're going to do this business, don't forget the interaction term when you're doing indicator variables. All right, otherwise you're really not doing much. Okay.
So the interaction is where we find it.
Yeah, that's where you find it. You got a different slope. All the slopes are the same for everybody except in San Diego. Actually, all the slopes are the same here. There's basically no slope in the x2 direction. Okay. So all these three planes are all the same, and they're all such that it's just z equals So there's no pitch in the y direction or x2 direction, okay, at all. All right, so they're all planes parallel to the x2 axis. And then what you have is that except in San Diego, okay, then that's a different one, okay. All right. That's why I took a couple points. Okay, it's just for reminders so we don't get the problem wrong again. Okay, but yeah, I mean it was kind of inconvenient because it was almost more like a problem chapter 9 question because there's so many terms in the model. There are 12 terms, including the intercept. So you have the 2 variables, the 3 indicators. Then you have 2 times 3 is 6 extra interaction terms, plus the intercept now. So there's 12 terms in the model, including intercept, like you said. And that's getting to be a lot of terms.
You would need to be x1, x2 intercept.
No, not unless you're going to look at a quadratic fit or something, if the residuals still look lousy or something like that. Okay, this is just to get all the different responses in the different cities. You know, you're allowing for different response surfaces, different slopes to the planes and stuff like that. Okay. So San Diego basically stuck out like a sore thumb. That's what happened.
You would have thought it would have been.
If it wasn't as easy to draw a picture, you could draw a picture in 3 dimensions to show this. Because you could do the scatter plot in 3 dimensions. That would just be possible in this example. I didn't do that. I don't think Excel does a scatter plot in 3 dimensions. It only does 2 dimensions, yeah. So you have to go to Maple to do it. Get the 3 different cities. Of course, Minneapolis doesn't really count because it only had 2 data points, but you could do that. But I did appreciate the other analysis that I got. People, at least one person studied how the variances were, the different cities and so on. So, and there was that question whether I think most people took at least the question as to does the city matter? Does the intercept matter at least? And you can calculate by the extra sum of squares method. Yes, it was okay to go ahead and take the quote-unquote full model, which was only involving change of intercept, and then set all the intercepts to 0 and see if there was any effect there. And there really wasn't much effect there. Okay. All the change of intercepts to 0. Okay. So that wasn't the problem. The problem was the slope. Okay, change of slope. All right. Well, anyway, thank you for your efforts. What about your questions now about Chapter 7? Chapter 7, I don't think there was too much problems there, actually. 716 and 718. People were getting that problem. I don't see if they have any comments about it. No. The only thing that bugged me was that I didn't see any calculations for how you actually got the confidence intervals. They were all correct. Okay. All the confidence intervals. So, but if I don't see any calculations, then how many digits am I going to take it out to check to see whether you got it right? Usually not very many. Okay. But I would appreciate showing the calculations. You will need to show the calculations on your final exam. Okay. So the way the final exam will go is, I think I mentioned already, it's pretty much show me how you do the calculations on everything. And then a little interpretation as well. Okay.
I have a question about
Yeah.
Is there any direction we should look in with a graduate problem on the final?
I didn't assign one. Okay. I think I mentioned mobile something about putting just a hand calculation for least squares on there. For the graduate problem, what have I seen? I've seen a couple interesting ones. If I could put another problem on there, that would be a good idea, probably. I didn't stick one on there yet, but should I do that? Yeah, kind of. Well, there was one with, two-way analysis of variance. I didn't put anything on about analysis of variance. Okay. That would be one direction to go. Chapter 12. In Chapter 7, there might have been something.
Post it for us.
710 is kind of related, but I've assigned it to everybody. See if there's anything in Chapter 12. I don't think so. Not that I really want to assign. Okay. No, I think you're off the hook. No graduate problem. Does that make it fair? Everybody's kind of in the same boat now. I could always assign that problem again that I gave you, 8.9, and finish it up, right? We could go over that problem a little bit now. How does 8.9 go if you actually do it right? Is there anything that goes wrong or goes right about it? I think it's okay, everybody wrote down the X matrix correctly. So 8.9 was, suppose I have one-way analysis of variance. And I have the following situation. I have 4 treatment categories. And then I have the data like this, y11, y12, y13. So n1 is equal to 3, or na is equal to 3. I have 3 observations under treatment conditions A. I have 2 observations under treatment conditions B. I'm going to use the capital letters just because it's easier to keep track of the indices that way. All right. I have 4 observations under treatment condition C. I'll still use the index here on the y's. N sub C equals 3. And I have 3 observations under treatment condition D. N sub D equals 3. Okay? I could have called this A1, A2, etc. Okay. A3. Maybe I will. If I'm going to go ahead, I might as well go full bore on the change of notation. Okay, C1, C2, C3, C4, and D1, D2, D4. D3, excuse me. All right? So there's the notation, and the question is, it's kind of an open-ended question. That was a bit of a thing, but can anything go wrong if it's not balanced data? So it's not the equal number of observations in each cell, so-called. Suppose that a one-way analysis of variance involves 4 treatments, but a different number of observations has been taken under each treatment. These are called cells. Okay. Where you consider cross-classifications of treatments. Here there's only one classification of treatments. All right. But in general you could talk about cells. Assuming these numbers of observations per cell, write down the y vector and x matrix for analyzing these data as a multiple regression model. Are there any complications introduced by the unbalanced nature of this data? I think what that meant was just go ahead and calculate what beta hat should be using the normal equations. You go through and figure out what SS res. I mean, if you finish the problem nicely, you go ahead and find out formulas for SSR, SS res, all that stuff, and give a little example in the end. Okay? Well, that's what we'll do. Okay, make sure we understand it. Okay? So, how does it work down then? So what's the Y matrix? Y matrix is therefore Y, A1, Y, A2, Y, A3, and then Y, B1, Y, B2, Y, B, YC, YC1, YC2, YC3, YC4, and YD1, YD2, YD3. Okay. And then the X matrix, what do you do? What are you going to have? You're going to have beta parameters beta 0, beta 1, beta 2, and beta 3. And the way we're going to model it is that mu 1, I guess now here's where, or mu A is beta 0 plus beta 1. That was the way the author suggested to do this. Mu B is equal to beta 0 plus beta 2. Mu C is equal to beta 0 plus beta 3. And mu D is equal to beta 0 plus beta 0 period. Okay. That was the model for me. To have, I'm going to, for the full model, I'm going to assume just a different mean for each cell. So what would the X matrix mean? It's basically just copy. Look at the situation. Here I'm in cell A. Here I'm in cell B. Here I'm in cell C. And here I'm in cell D. Okay. And so let's see. If I'm in cell A, then I need. So really, what I have is mu. So if I want to fill this in, I have mu A, mu A, mu A. All right, for the mean. So the mean, if you want to write it down like this, is mu A, mu A, mu A. Okay. All right. And then mu B, mu B. So actually, these equations, I'd have to repeat them several times depending on how many times I had an observation in the cell. Okay, to get the full vector of means. That's the model for means. Model for means. This is one way of expressing it, and then in terms of the X matrix, it's in other words, expressing it as X times beta, a vector of parameters. It's 1, 1, 1. You put coefficients on the for the betas, okay, here, and then there's nothing here, okay. And then you put 1, 1, 1, 0, 0. I'm sorry, there's only 2 zeros there. You did this correctly, I believe, in your homework. Okay. Then you had 1, 1, 1, 1. Zeros here. 1, 1, 1, 1. And then finally, just ones here. And then all these are zeros. So if I actually write down X beta, then X times beta therefore looks like, where beta is beta 0, beta 1, beta 2, and beta 3. X beta therefore looks like, what does it look like? X beta therefore looks like beta 0 plus beta 1, beta 0 plus beta 1, beta 0 plus beta 1, and then it looks like beta 0 plus beta 2, beta 0 plus beta 2, and then it looks like beta 0 plus beta 3 4 times, etc. And then finally it just looks like beta 0, beta 0, beta 0. Okay? So that's actually what it looks like. Now, so let's solve the normal equations then. What are the normal equations? Normal equations are beta hat equals x prime x inverse x prime y. But there's maybe an easier way to solve these. I don't want to take an inverse of a matrix. Otherwise, this is known as x prime x beta hat equals x prime y. Okay, so let's go back to this because it's actually easier to solve the normal equations directly. In fact, it's kind of intuitively obvious how to do that. Because what should mu a hat be? It should just be the average of these y's. Okay, that's intuitively obvious from our knowledge of how to minimize sums of squares. How do I minimize the sum of squared deviations? This is going way back to the first day. If I have to if I have to minimize summation yi minus c squared, what do I choose for c? I goes from 1 to k. What if I've got something like that? What do I choose for the c? If I just have a bunch of y values and I'm trying to approximate them by a single number, okay, that's like just taking the intercept. I'm just trying to get a straight line, horizontal line. If I had, in other words, if I had a bunch of, well, I guess you think about it, these y values are not associated with any x values at all, okay? So you just have a bunch of numbers on a horizontal line, a y-axis. If I got a bunch of numbers on a horizontal axis, y here, what number c should I choose so that I minimize the sum of squared deviations? Remember that stuff? Okay, well, yeah, the mean. Okay, c equals the mean, y bar, okay, is what does the job. Check that out. d by dc of summation yi minus c squared equals minus 2 summation yi minus c. That equals 0 if and only if nc or kc equals summation yi. Okay, I goes from 1 to k. If and only if c equals y bar. Okay? Equals 0 if and only if. Oh, okay. So that's the basic fact. Okay? That the average minimizes that. So if I wanted to minimize the sum of squared deviations where I'm allowing a different parameter, basically in each of these blocks. All right, so I want to minimize now summation I goes from a to d, and then j goes from 1 to n sub I, okay, minus mu sub I. That's what I've got here. I better leave more room so I can read this. Minimize, because I'm trying to minimize what? The y minus the mean of that y. Right? In the model for means. And this model for means is just a mu I when I is in the, when j is in the, ij is in the ith block. I goes from a to d, j goes from 1 to n sub I. I'm looking at this squared. Okay, minimize this over mu A, mu B, mu C, and mu D. How am I going to do that? Well, that's trivial, because as long as I minimize each of these inner sums of squares, I've minimized the total sum of squares. So I just minimize each one of them individually. So mu A hat is y A bar. All right? Mu B hat is yb bar. What I've done is that before I actually solve this normal equations, I'm just going back to what I should know. Mu C hat equals yc bar. Okay, and mu D hat equals yd bar. This is going back to just filling in some basic facts about statistics, okay? That we should know in this context, that you should really know. Okay? So now, let's go ahead and look at this normal equation. That should just give then, okay, that this equation, therefore, okay, beta 0 hat plus beta 1 hat should equal y a bar, right, and all that stuff. Let's just double check, make sure that's coming out in the normal equation. This is just kind of playing with it. It's obvious that that's got to be the way it's going to be. What is x prime x? X prime x is 12. Let's see, how do you do x prime x? Remember how I said to do it? Take this column into itself, that's 12. This column into this column, this column into this column, this column into this column as inner products. So that's 12, 3, 2, 4. It's symmetric, so I get 12, 3, 2, 4. Then I take the second column into the first, second, third, and fourth. Okay, so I get 3, 3, 0, 0. 3, 3, 0, 0. And then you can see you're getting this 2, 0, 0, 0. You're just getting a diagonal matrix for the last part, the last block of this matrix. Okay, that's x prime x. And then x prime x, okay, so then I want to solve, and what x prime y is easy enough. X prime y is what we call, let's see, x prime, I'm summing all the y's. When I put this thing on its side and I multiply it against the y, I get what I call y double dot. Okay, sum over all the y's. Then I get, when I put this thing on the side and I multiply this against the y's, I'm just getting y a dot, y b dot, and y c dot. I don't get any y d dots here. Okay? Now what is true is that y double dot is not just the average of y a dot, y b dot, y c dot, and y d dot. It's a weighted average of those. Okay? But that's not going to play in too much if we do this. Okay, so let's just see what happens. So then what you get, so the normal equation comes out to be, what? You get 12 beta 0 hat plus 3 beta 1 hat plus 2 beta 2 hat plus 4 beta 3 hat is equal to y double dot. You get 3 beta 0 hat plus 3 beta 1 hat equals y a dot. You get 2 beta 0 hat plus 2 beta 2 hat equals y b dot. And you get 4 beta 0 hat plus 4 beta 3 hat equals y c dot. Okay. So what do you get? How do you solve those equations? Those are the normal equations. You know how to do it because you did it, right? One of you did it. Okay. Or at least you looked at the normal equations, but I don't know if you solved them. Okay, so let's see. Do they solve out exactly the same way? Yes, pretty much. You subtract these first. You subtract all these rows from the first row. What do you get? You get the first one. You get beta 0 hat. You get 3 beta 0 hat. Let's see. Now what is it? 5 and 4 is 9. 12 minus 9 is 3. Beta 0 hat equals y double dot minus y a dot minus y b dot minus y c dot, which is equal to y d dot. Because this is the sum of all the y's, this is the sum of the other ones that don't involve the d. Okay. And so you get that beta 0 hat is indeed, since there are 3 observations in the dth cell, this comes out to yd dot bar. Okay? Or I would just call it yd bar. Okay? Usually they put the dot there too. Okay? And then you can solve for the other ones. So what does beta 1 hat come out to be then? It's beta 1 hat is y a dot minus, then you multiply back 3 beta, or you just use a 3 beta naught hat is y d dot. Okay, so you get 3 beta 1 hat. Beta 1 hat is therefore y a dot minus y d dot divided by 3, which turns out to simply be y a dot bar minus y d dot bar. Okay, which is what you'd expect, because we saw that beta 1 was mu d minus mu a, mu d hat was y d bar, and mu a hat was y a bar, so that you're getting exactly what you'd expect. In fact, you could argue, because of the linearity and the relationships between the mu's and the betas, that's exactly what you'd have to get. Just solve those equations, then get the hats for the betas by putting the hats on the mu's. So it's kind of trivial in that way. Okay, that what has to happen does happen. And the only thing that you might go through after that is calculating the regression sum of squares and so on and so forth, and calculating little formulas that relate all these things down. What you have is that SS res is simply obtained by taking these mu hats, okay, and sticking them in to the formula that I erased now. So SS res is simply going to be summation, double summation yij minus y I dot bar, okay, squared. J and I goes from A to D, J goes from 1 to n sub I, okay? Because these are the mu hats. And you can write it down in terms of the betas if you want. But that's not necessary, okay? Because this is mu hat. And what you do is you take whatever you've estimated for your means under the model for means, and you put them in that sum of squares. That's the way you've always do it. Okay, whatever your model for means is, you estimate those. We had the y hat, right? We put y hat in, but that's your estimate for expectation of y at x. Your estimate for expectation of y at x in this situation is simply these different constants. So this plays the role of EY given x. For x equals 1, 2, 3, it's one thing. For x equals 4, 5, it's a different thing. Okay, for x equals 6, 7, 8, 9 is a different thing. All right? So it's like EY given x is like a step function. Okay? If you're getting my meaning, it's one thing here when x is, and then it's another thing here, and then it's another thing here, and then finally it's another thing here. Okay? Okay. These x runs along from the first to the, or it's from the first to the 12th observation. There's no x, right? This first observation to the 12th observation. But you can think of x as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 if you want. In that case, then you'd have, this is your model for means. It's just a step function. Okay, if you want to put x as the observation number. Okay. So all you do is you stick in your estimate. All right, that's SS res. That's always the definition for it. And then what's your regression sum of squares? Regression sum of squares, you could get it from the totals, from the corrected total if you want. So, because what is the regression sum of squares? What we're going to do is we're going to have a reduced model. What is the reduced model? I always need a reduced model. I have the full model. I need a reduced model to get a regression sum of squares. What's the reduced model? Okay, the model for means is just that's usually just everything a constant. In other words, all the beta 1, beta 2, beta 3 equal to 0. Okay? Which corresponds to all the taus equal to 0 under the little bit more symmetric looking model for means that they offer in the book. Okay? So these three are all 0, but the beta 0 is not 0. And so what's then the error sum of squares for that thing? So SS res of the reduced model. This is of the full model, SS res. What's the SS res of the reduced model? that's going to be, well, now mu hat is just going to be, now mu is going to be constant here. So what's going to be the obvious, if you're going to, the sum of squares is just, there's no double sum, it's just a single sum. Summation yi minus mu. Right? So then mu hat's simply going to be, well, I'll still write it as a double sum. So as the reduced model sum of squares is like that. So the regression sum of squares, so I'm trying to unify this whole thing so you understand kind of like a review of the whole thing. What are the regression sum of squares and so on and so forth. It really is, what you're really doing is you're passing to a reduced model. And okay, so there's that. And so how do you take the difference of those two? So SSR of beta 0, beta 1, beta 2, beta 3 after beta 0 is a notation for the difference of those two things. That's SS res full. Excuse me, reduced model minus full. All right, and this is actually also what we call total sum of squares. This is SST corrected. Okay? Because that's always what it is when you just have the constant model for means. SS res reduced model minus the SS res full model. Okay, so what do you figure the formula is? Is there a nice formula for it? Take the difference of those two. I guess we could go back to the beta hats, and x prime x inverse, and all that stuff too. Which is what he does. He actually goes, the author does this without subtracting the beta 0 thing. Okay? So he calculates this. Alright, with a formula. If you look there on page 285, beta hat prime x prime y. This is another way to calculate this, is to take SSR of beta 0, beta 1, beta 2, and beta 3. Take all of them. If I was going to go to a 0 model, this is SS reduced model minus SS full model, where SS reduced model is where you put 0 here. Okay. In other words, we have the mean is 0. We're assuming that all the y's are 0. There's nothing to estimate. In that reduced model, super reduced model. Okay. So what is it? He puts this as beta hat prime x prime y, which you can actually calculate in this way, and it comes out exactly the same type of formula, only it's not, it's not quite as symmetric. It comes out x prime y was here, n. Let's see, how does it come out? It comes out. I'm sorry, this is not the same as this. This is minus. Let's put it this way. Oh well. What this is SSR beta 0, beta 1, beta 2, beta 3 minus SSR beta 0. Okay, we only have a beta 0 in the model. So you can calculate it that way, and he does that in the book. Okay, for his example, in the balance case. That's the way he's done it. What did he do? Well, so this comes out to be the full model, and so I'll just write it down. Take this away. This is a little bit confusing, but this is his SSR notation. The formula for SSR beta 0, beta 1, beta 2, beta 3. He puts hats on there, but I don't think that was necessary to put the hats inside there. Regression sum of squares due to those fitting those parameters. This is beta hat prime under the full model. Okay, full model beta hat prime. X prime y. Everything full here. Okay, so what does that come out? Here are my beta hats. There's my x prime y. So that comes out y d bar times times y double dot plus y a bar minus y d bar times the next one, which was y a dot, plus y b bar minus y d bar times y b dot plus y c bar. I didn't write all the beta hats down, but this is what they are: y c bar minus y d bar times y c dot. Okay, it's just this. This is a sideways vector, which is this beta hat sideways, times this column here. Okay, and so you actually get a formula for it. And if the way you can do that is write down y double dot is NAY A bar plus N2. So y double dot is NA times y A bar plus NB times y B bar plus NC times y C bar plus ND times y D bar. Okay, and similarly you can write y A dot is NA times y A bar. Okay, so plugging in all those, some nice things happen. What happens is that this y D bar times y double dot, it cancels all this stuff. The y D bar times the y A dot, the y D bar times the y B dot. Maybe it's easier just to say y double dot is y A dot plus y B dot plus y C dot plus y D dot. Okay? So, y equals y A dot plus y. I think it's just a matter of how you're writing it down to make it the easiest. So this term cancels these terms, and then there's one term left over, namely the yd times yd dot. So what you get is y a bar times y a dot plus y b bar times y b dot plus y c bar times y c dot plus y, the last term that didn't get canceled, y d bar times y d dot, which is summation ni y bar I squared, like that. I goes from A to D. Okay, so that's the regression sum of squares, but not corrected for the mean. Not corrected for the mean. This is uncorrected. Not corrected for the mean. And the way to correct it for the mean is to subtract something from it. Okay. So maybe I should give you an example. What's this SSR beta 0? That's simply just beta hat. Okay. If this is this fully reduced model thing, so if I do the same calculation, only now beta hat is going to be what? It's simply going to be beta 0 hat, which is simply going to be y double dot bar. And x prime is simply going to be a column of ones. X is going to be a column of ones, x prime is going to be a row of ones, and y is simply going to be the column of y. So this little devil, SSR beta naught, is simply equal to y double dot bar, that's the beta naught hat, times y double dot, okay, equals n y double dot bar squared, okay. That's the usual thing you subtract off. Okay, so that's, if I subtract that off, then I get the corrected total, and that's what this SS regression sum of squares is, the usual one. So then I get, let's just put an example here where you can see all the numbers, so you can see how this works out. So you have, let's take the example of the data is 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 11, 12. So these are the y's. And then the y1, ya dot bar is equal to 2, yb dot bar is equal to 5, y3 dot, or c dot bar is equal to 8, yd dot bar is equal to 11. The way I set it up here. Okay. What's the SS-Res full model? SS-Res full model is simple to get because I'm just taking the deviations from 2 in this first block. So that's 1 squared plus 0 squared plus 1 squared. That's 2. The deviations from 5 are 1 and 1. So those square add up to 2. I get 2 also from this contribution, and I get 1 plus 0 plus 0 plus 1. Again, 2 from there. So SS-Res full model is 2 plus 2 plus 2 plus 2 equals 8. Okay. See how that's working out? What I'm doing is I'm taking summation. I'm taking 1 minus 2 squared plus 2 minus 2 squared plus 3 minus 2 squared. From this, and that gives you 1 plus 0 plus 1, okay? Which is 2 from this block. Remember that? Here I had SS-Res is this. So I'm just taking the sum of squares, pooled sum of squares. Okay? It's a pooled idea. All right? And then you have, what is it now? SS, that was SS-Res full model. Okay? Also, you'll notice that y double dot bar, if you add up all these numbers, it adds up to 84. 84 divided by 12, you get 7. Okay, so that comes up to a nice integer too. Okay. So what do we get? So what do we get for SSR? Beta 0, beta 1, beta 2, beta 3. Uncorrected. Okay, this comes out to be, according to that formula, the last one I got was 3 times 2 squared plus 2 times 5 squared plus 3 times 8 squared plus 4 times 11 squared is equal to 738. Okay. And what's the SSR for beta 0? In other words, the correction term, that's ny double dot bar squared equals 12 times 7 squared. That's equal to 12 times 49 is 588. So what does that mean the usual regression sum of squares is? Usual regression sum of squares, which is the difference of those two. So SSR with no notation is the 738 minus the 588 equals 150. Okay. And let's check that what the total sum of squares is. And so then you should have that, what you should have is that the corrected total plus SS-Res is the sum of SS-Res full model plus this one, right? So what I should have is I should have SS-Res full model is 8. I should have, res. I should have SSR for beta 1 equals beta 2 equals beta 3 equals to 0, okay, corresponding to the hypothesis, beta is all equal to 0. This comes out to be 150, okay. And then my SST, what's my corrected total sum of squares? Well, now I would subtract each of these numbers from 7, right? Take the sum of squares. And that's not that hard to calculate. Here it is. SST corrected is 36 plus 25 plus 16 plus 9 plus 1 plus 0 plus 1 plus 4 plus 9 plus 16 plus 16 plus 25 equals 158. Okay, it does work out. Okay. I know that's a lot of a lot of arithmetic. What I'm doing is I'm taking 1 minus 7, the way I'm doing it, 1 minus 7, 2 minus 7, 3 minus 7, 4 minus 7, and squaring each of those. 7 minus 7 is 0. That's where the 0 came from. Okay, so it adds up. Okay. And then, of course, the degrees of freedom, one of the mean squares. The mean squares would be 150 divided by 3 equals 50. And how many degrees of freedom less for error? Okay. There are 11 total after the correction. 3 used here, so that's 8. So mean square here is 8 divided by 8 equals 1. Degrees of freedom were 3, 8, and 11. Degrees of freedom 3, 8, and 11. Okay. Well, anyway, that's how you do it for there. So I guess the answer is there's not a whole lot of difference except what is SSR? SSR, the formula for it is summation NI yi dot bar minus y double dot bar. I believe this is the square. This is the between groups variability. That's the formula for it. So he actually, that's how you would generalize it. Whereas I think before he just had it was the common number n times. So this double sum. What page was that? Are you looking at it? Does he have that formula in there for SSR? Yes, he does on 821. This is the analog of 821. So it wouldn't be very difficult to guess. Okay. This is the analog of 821. Page 286. Okay. So that's how you really do problem 8.9. Okay. You just go through the whole thing and remember what everything is. It's just a really good review of regression, how the whole thing takes. I think, even though you're used to having x's and linear functions and quadratic functions and so on. So there's a little bit of analysis of variance. Then you get the two-way analysis of variance, which you just barely touched on that one day in lecture. They asked you to do a problem there. I think I'm going to steer away from that, though, for the final. Not asking anything about that. Anything else I ask is going to be pretty much extra credit of what I've already asked on the document there that I said we would do for the test. Questions now? What about 9.4? Are you satisfied with what you got on there? What was your best model? Was there only one candidate model? One candidate. If you used Fn equals F out equals 3, right? What did you get? Did you get more than one candidate? Three different candidates.
Yeah, three. I get 3 different candidates.
got it. No, when I did, all of the regressions or whatever, I got all the regressors in, gave the lowest CP and the lowest MS-Res.
Oh, really?
Yeah.
I didn't get that.
The lowest CP was with all of them? No, CP was 6 with all of them. CP is 6 with all of them. There was one with 5.8 or something.
Yeah, so I got 4, 1, 2, 3, 4.
Okay, CP for the maximum for the full model is always just the number of columns of the X matrix. So there were 5 regressors and 1 intercept. So CP has to be 6 for that. So it was nearly the smallest CP. So it was nearly all of them. But I think the backward regression would take out X5, I believe.
Yeah.
Okay.
Definitely.
Yeah, I probably put something wrong with my form because I kept looking at that and all the other ones with the, when you do FN3, FOut3, come up with the same thing. And I think that CP was like 5 point something.
Yeah, so this.
Coming up with a 4 with the full amount.
Okay, so there was some mistake, a little mistake there. Okay, well, yeah, so I'm not going to have time to correct it. Yeah. You can look on the website now, because I just stuck my solution 9.4 up there, just in case you wanted to look at it.
So will we get those back?
Yeah, I'll give them back.
Right, yeah, so that must have been in my formula. I had a formula I just dragged down.
Okay.
So it had to be there.
How was it doing all the regressions? Was that bad? No. The thing is that my hint was first do this forward, stepwise, and backward, and then use that little trick with the correlations. You practically have all the regressions done already.
Yeah, most of them were.
Most of them were done. You got a few left.
I only had probably did about 5 or 6.
Okay. Well, luckily you won't have to use Excel at all for the final, but.
I know it's interesting the 9 points.
Okay, go ahead.
Having them like statistical typology.
Yeah.
When you pick your hypothesis, you're always picking your confidence interval, basically your alpha up front.
Yeah.
And so kind of what I was looking at is when you're doing the stepwise regression and stuff, when you get down to a T statistic, like I had one, what was it? I forget what variable it was, but it was like 1.97. Depending upon what I picked my alpha, I may or may not throw that out.
Yeah.
So I may even reduce it down more than what it was.
Yeah. That's true. It was pretty subjective. That's why the author suggests comparing models not only on that basis, but then start getting the press residuals out and so on.
Right.
How good is it for predicting? And get multiple measures to analyze, to compare the models, and that's what Part E was about. Get a few candidate models and start comparing them. That's a reasonable thing to do. And it would have been fun to spend a little bit more time doing that. We can do it now if you want. See, it's very simple to calculate the press residuals, right? That's not difficult. You just have to write a few things down. But you have to, depending on how many variables in the model, the HIIs change. You have to take the candidate model. Since I only got one candidate, I didn't have to do it. And I chose my F min equals F out. So there's nothing to compare it to. That's the best model. Wasn't it the min CP too? Or was it not? I don't think it was a minimum CP model. Just all 4, X1, X2, X3, X4.
That was the min CP.
It was a min CP model. So then the only question is whether it was also min MS res. Was it also min MS res?
Yes.
Okay, so then there was nothing.
No, it wasn't.
Oh, it wasn't.
Min R squared, but not min MS res.
Yeah, I think the minimum MS res was the full model.
Okay.
I've got them highlighted on mine.
Okay, so that wouldn't be too difficult to compare those then. Okay. Okay. Recommended for all regressions best in lowest CP and highest RP. The y hat was the just a 4 variables model. Lowest CP and highest RP squared, but what about the adjusted RP squared?
Is that it? Or am I going to
Okay, well, you've got the whole thing done anyway. Okay, so the minimum MS res was yes for all 5 regressors. So we could compare all 5 regressors versus just the first 4 regressors with press residuals and see which one that worked out better. Okay? Yeah, that's very nice. Nice job. Excellent job. I'm going to photocopy that and save it for the next time I teach the course. Okay. My solution. I'm teasing you. Well, did you do the extra credit part too?
I did not.
You did not. You didn't do it.
Well, I made a comment, but I didn't do it.
Got tired of it. I was doing it until about 1 or 2 in the morning.
Okay. That wouldn't be that much more work, actually, would it?
Yeah.
So just all 5 regressors versus just all the first 4? So what do you need to do? Yeah, you just need to do 2 more regressions, right? And then do the 2 x prime x. What do you need? You need. So what will we do? What will we do if we were going to do this? Which we could probably do in 10 minutes, right? You have your x full, okay, which is n by 6, and this is regressors x1 through x5. This is on 9.4. Well, you've got the 2 candidate models, an x1 through x5 and x1 through x4. Okay, and so x reduced model is n by 5. Okay, and so let's just call it x sub r. Okay, and x. Okay, and so then you have. So you have to calculate x prime x, which is a 6 by 6 matrix. So with your m multi, you have to calculate x r prime x r, 5 by 5. And you have to take the inverse, 6 by 6, and you have to take the inverse here. Or what's an easier way to do that? Yeah, you still have to take the inverses. And then you have to calculate the diagonal of the hat matrix. There's an easy way to do that. I think the easiest way to do that was the way that Shane suggested, which was to take, well, I don't know, I guess you can do it in a pull-down formula. I think you can do it in a pull-down formula. I'm not sure if you can or not. Yeah, I think you can maybe. So what you do is you take the x, you basically take xi, which is written down 1 x1 xi1 over to xi6. This is the HII for the full model. You take this vector, which is a horizontal vector, you multiply it times that matrix, which you have to reference. Okay, let's reference that one. Times the reference for x prime x inverse. Okay, and then times the transpose of this one. Okay? Okay, xi5, I'm sorry. Okay, and then, so that's with an m mult, okay? But then actually when you, okay, so then you get that thing, but you can actually pull down, I believe, the array formula, okay, in Excel. Reasonably certain. Maybe you can't. I can't remember if you can or not. If you can't, then you have to go back to the other method we used for calculating it. Take the H matrix and take the diagonal down. Okay? Has anybody tried it this way? Okay. Okay. And that gives you the little HII of that product. Okay. And then you calculate the press residuals. Then you have the residuals. Then you have the press residuals, which are EI over 1 minus HII. And you do that for each model. And then you take the sum of the squares. And then you take the press statistic, which is the sum of the squares, EI over 1 minus HII squared. And whichever is smaller, you say, well, that's a little bit better model. Okay? Or you can also look at the variance inflation factors. That was another thing you suggested. So for that, you would take the diagonal of the you'd have to find the correlation matrix first, all right, for the regressors, and then take the diagonal of the inverse of that. So, I mean, it takes you 25 minutes pointing and clicking. Remember that? So for the VIFs, the calculation is to take the correlation of the regressors. Correlations of regressors only. All right? Correlations of regressors only, and take the inverse matrix. And then take the diagonal of that. Okay. And so you could say which one has more multicollinearity. If the VIFs, obviously, since one model is a subset of the other, okay, if there's the same about if adding x5 doesn't increase any of the VIFs, then we say, okay, that the VIF criterion is basically gone. We don't have to worry about it. If it does add some multicollinearity, then you say, okay, then that's a consideration. Especially if the maximum VIF goes up by a factor of 2 or something. Okay. So, and then the press, well, then you see, well, are they 99% the same? I mean, within 1%, are they the same or not? Something like that. So anyway, I think we'll skip the calculation, but at least that would be what you could do. Any comments about that? Further comments? Okay. Want to do logistic regression for half an hour? Should we take a 5-minute break? Let's do half an hour of logistic. There'll be one last example, which won't be required for anything. Then you can take your quiz here. Faculty course questionnaire. What do you say? Do you have more questions? You just want to go home? Go home early? Let's get out of here. Take this thing and run? Okay. This is not televised, right? No, Nick, that's fine. Logistic regression. I did have some notes on that. It was kind of, maybe I should just go through it real quickly here, and then we'll go. Then we'll just give this out. You still have 10 minutes on the thing? 19. Wow. We got lots of time. Don't burn it too badly.
6 minutes for you.
Okay, that's true. Let's break it down to 6 minutes. That's right. It's the 3-to-1 ratio. Let's talk a little bit. Well, I'm not going to be able to give you the lecture on logistic regression. I'll only be able to give you the sheet. Oh, it's like, okay. There's no way I'm going to be able to do that in 19 minutes. Let me just give you the short version then. Okay, maybe I can do it in 18 minutes. Like you said, 1 minute for each 3. Okay. I'll just go ahead and give you the notes since I've already printed them off. Logistic regression on proportions. Okay. Yeah. I just wanted to show you one thing with the calculation, because and this is a little bit about chapter 13, and then you pretty much have seen a lot of the book. You won't have seen everything in chapter 10, which is the multicollinearity chapter, though what he starts to talk about at the end of chapter 12 actually impinges on chapter 10. What we were doing in the nonlinear regression, which we went over a couple times, relates pretty closely to what's going on in chapter 10 if you, instead of using Z, let's see, what is it? Well, anyway, there's a trick. Let me just point out one thing in chapter 12 before we go on, in case you want to read this book some more. Yeah, Marquardt on Chapter 12 on nonlinear regression. Marquardt considers, I think that's how you spell it. Yeah. Marquardt has suggested the following. Instead of using z prime z beta hat equals z prime y, this is the vector of increments in updating theta hat. Okay? Then what you had was you had something like you had an E here. You had a Y minus F of theta hat X and theta hat K. All right, this is what you had here. So this was the method. Remember, this is what we called the error vector. Okay. He suggests instead of using this, which is what we did, which is what we're doing with Excel. This is what we're doing. Where this was the latest update in the Z matrix, the columns of Z, which were the partial derivatives of the regression function evaluated at the latest value of theta. Instead of doing that, he suggests as biasing the situation a little bit by putting in a small parameter here. So putting in something that's non-zero times the identity matrix here. I sub p. This is a p by p matrix. Okay, so that's Marquardt's method, which is very closely related to the ridge regression in Chapter 10. And what the author was saying is that, okay, the convergence for the Gauss-Newton is pretty quick. Okay, the convergence for the steepest descent method is not so quick, but at least gets you going in the right direction. There's another method that you'll find on big computing packages. And this kind of compromises between the two. So that if you don't have a good initial guess, you can just take basically any starting guess and take a very small lambda. So what he was suggesting is that, anyway, there's a kind of an automatic procedure based on this compromise approach, which is used in the Statistical Analysis System, for example, SAS, because they can fully automatize the problem of doing nonlinear regression. What they do is they take a very small lambda, I think they mentioned lambda equal 10 to the minus 8 or something, and see if your S theta hat is getting smaller or not. Okay? And then if it is, okay, then they bump it up by a factor of 10. Okay, take lambda equals 10 to the minus 7 and see if S theta hat is getting smaller. Okay? This kind of thing. So they can actually, by various devices, actually get an automatic system. So you don't have to do it by hand with this method. So anyway, that's kind of a numerical comment. That was 2 of my 6 minutes. Okay, so I just thought I'd point that out. We're not going to be tested on it. I just thought if you really want to read this book. And then what he goes on to in Chapter 13. So I'm not going over Chapter 10. That's the one thing we skipped by trying to cover a little bit of 12 and 13. And 11 is junk. Okay, so 13 is about nonlinear regression and a generalized approach to the regression. So that'll handle all kinds of errors, not just normal errors, but anything in the so-called exponential family. Exponential family includes the binomial Poisson, gamma. I believe gamma is in there too. Okay, and normal, of course. And he doesn't really show you how he's doing the computations in Chapter 13, so I thought I would give you a quick introduction to how you do iteratively reweighted least squares. We already talked about weighted least squares where you iterate it. Okay. But in the case of logistic regression, there's kind of a standard thing you do. Okay. What you have is you have is you have data, the data Y consists of counts. And some examples are the pneumoconiosis data. I don't know what pneumoconiosis is, but apparently it's something that miners get when they breathe too much coal dust. Something like probably pneumonia, that they can't get rid of. Okay. And what they have is a number of severe cases that count, okay, among a total number of miners, and it has by years of exposure. So they have a group of miners that were exposed for about 6 years. They have a group of miners that was exposed for about 15 years, and so on up to 50 years. And those groups have sizes. So you have number of cases, okay, and then the total number of miners in the group, which is given by years of exposure. So that would be your X. Okay, 5.8, 15.0, 21.5. Gosh, some of these miners worked a long time, up to 51.5 years. Okay? Number of cases 0, 1, 3, 8, and so on. But then the total number of miners was 98 in the first group, 54 in the second group, 43 in the third group, and so on. This is the number of miners that they had in their experimental result. So they somehow were able to sample 98 miners who had worked for 6 years, and they found out that none of them had the severe case. But out of the miners who worked 15 years, where they had 54 of them, one of them had a severe case, and so on. So these are count data. Another example I referred to in the notes was, let's look at problem 13.3. Actually, I didn't. If you look at those notes on the very bottom of the page, there's a couple blank spots where I was referring to, because these are old notes that I was doctoring. Okay, so it says, because there was a second edition where this is actually in chapter 6, this whole business, in the second edition. Okay. So, for example, on page 479, problem 13.3 on page 479. That's the blanks on the bottom of these notes. So, for example, in page 479, problem 13.3, you've got another example where you've got a certain kind of fasteners using aircraft construction, and you have the load being put on the fastener. That's your X, not the number of years of exposure, but the load being put on the fastener. Fasteners are like screws or things, but nails. Okay, but here I don't know what the fastener is. Okay, the load being put on it, and then you have the number of different samples you studied. Okay, for the load being put on, and then the number of failing. So you have a certain failure rate, right? You had 10 failing out of 50, or then 17 failing out of 70 when the load was higher, 30 failing out of 100 when the load was even higher, and so on. Out of 51 failing out of 65 when the load was the highest. That's not too good. You wouldn't hope that that was happening on your airplane, but okay. But these are examples. Maybe these are the excessive loads, okay, when they're just studying the rate of failure. All right? So what is the model? We have to have, obviously, what you're going to be modeling is the rate. Okay, or the probability of failure, the probability of getting this disease, etc. Okay, so you're estimating your nonlinear regression is pi of x. Okay, is a probability. Okay, that's going to be the probability that the strength in a threshold model. In the threshold model, that would be the probability that the strength is less than or equal to X. Okay? The strength of the fastener, for example, in the fastener example. Okay? So it would actually be a cumulative distribution function evaluated at X. So the probability, in other words, this is in the fastener example, which isn't the same as this, because this is not exactly the same example, but still, you can think of it being a cumulative distribution function. All right? And so what I want normally is a cumulative distribution function kind of looks like this. Okay, the normal cumulative distribution function is symmetric and S-shaped like this. This is the CDF. Cumulative distribution function evaluated at X. That's what this is. Okay, so that's how I want my pi of X to roughly look like that. And there's two models. One is called probit, the other one is called logit, where they make different assumptions about what this curve actually is. There's going to be parameters in the curve. Well, what family? The one is it's just a normal cumulative distribution function. That's probit analysis. But the more common one is the logit example, where we assume this is a logistic curve. And so we assume that pi of X is of the form logistic model. The reason is that you can actually linearize the regression equation. Okay, logistic model is that this is e to the beta 0 plus beta 1x over 1 plus e to the beta 0 plus beta 1x. That's the common expression for a logistic curve, which I derived on the top of these notes. Okay? So I handed out. This is a differential equations problem. Do half a page. Okay? The logistic differential equation. So that's the model. Okay? So you're going to fit two parameters. That's obviously a nonlinear thing. So you're going to take, this is going to be your data. It's going to be the number of severe cases. You have both of these numbers, the number of cases and the actual sample size. So what kind of data is that? Well, it's actually binomial data. These are binomial counts. All right? So you have to bring in the variance and so on. So what you're going to do is to linearize this first. You're going to say, what's 1 minus pi of x? That turns out to be simply 1 over 1 plus e to the beta 0 plus beta 1x. Right? That's a pretty easy calculation. I think all your college algebra students could do that. If I take 1 minus this exponential, then getting, the common denominator. You're going to test that? Okay. See if they can deal with all these parameters and stuff. Okay? No, just take e to the a over 1 plus e to the a. Subtract it from 1. How's that? E to the a over 1 plus e to the a. Okay? 1 minus that. Test that theory. Okay. Okay. All right. So, anyway, that's what it comes out to be. And so that if I take the ratio of these two things, pi over 1 minus pi, I obtain e to the beta 0 plus beta 1x. So now I just take the log, and I get the e's and everything gone. I just get my linear regression function, right? Log pi over 1 minus pi equals beta 0 plus beta 1x. So that's linearizing. You get a natural estimate for pi of x. Pi hat of x is simply going to be the ratio of these numbers. 0 over 98, 1 over 54. That's kind of a bad one because that's extreme. 0 over 98. That's going to actually cause trouble. You got 5 minutes left? 3! Boy, I really do take a lot of time. Okay. Okay. Well, if we want to finish this little talk, we're going to have to take a break. I know you didn't want to do that. So what you do is you're going to regress this, the log of this. This is called the logit. You're going to regress the logit on beta 0 plus beta 1x. How are you going to get your beta 0 hat and your beta 1 hat? Done, right? No. Because, remember, this is the nonlinear function. And so we have to then update. Okay. But instead of using that other thing where you use the derivative and so on and so forth, there's a different approach. And that is because we actually know the approximate variance of this logit. Okay. Through the fact that we know exactly the variance of pi. Because that's a binomial variable. Okay. So we can do a weighted least squares approach. by you bringing in the weights. Okay, so instead of using the nonlinear regression approach, here we can just go directly to the weights, and that'll work. And then in chapter 13, there's I think they use both the weights and the nonlinear regression approach with the derivatives and so on, and combine them together, make it a little faster. Okay. But what's interesting in this problem is if we start here, then I don't know how are you going to start here? Because what's the logit of 0? The logit of 0 is the log of 0 over 1, okay, which is negative infinity. That's not a good number to put in my regression problem, okay? So I have to fudge, and I have to give this the initial pi a turn. Okay, so we have to turn the camera off. So why don't we take a break, and then we'll come back and do your evaluations. Or we can just turn the camera off now, okay?